you can reduce your costs and not produce a lot, and so maybe your profits are there, or you can increase your costs and get the best product and produce more. There's another approach. I would suggest that second approach. Try to get the best equipment, best technology, because technology has value. But optimize it, use the resources, have the sufficient knowledge, and then produce more. And there, you get better profit. Rather than trying to be conservative, I'm trying to be more dynamic. I'm trying to tell you to be more dynamic. Does it make sense?
One question which came to my mind is that, like the technology in terms of machine learning and AI, it's changing very rapidly. It's just like mobile phones in 2010 when there were touch screen phones and they skyrocketed. Now every phone is same.
Yeah.
Now the technology is changing so fast within the AI journal. Like today I invest into AI latest technology, and the next day it gets outdated now. So what do you suggest in those case scenario? How to balance out these investments?
Why don't you remind me the same question in the afternoon session? We might finish in the afternoon session. We may have 30 minutes. We can talk about AI and stuff like that, and how that automation technology can really play it. You're going to learn actually something, but let's park that question for that afternoon session so we can finish. I think we have everybody right for this room. So let's start this. But do ask me that. Okay, so greenhouse heating, right? We talked about cooling. In some rare situations, you may have to heat a greenhouse, especially if you're up north in Kashmir. Let's say that. Okay, or maybe in mountains and hills where it can get really cold, freezing cold, like 0 degrees Celsius in winter. I told you 25 degrees Celsius is optimum for crops. Outside air is 0 degrees Celsius. Of course, the greenhouse will increase the temperature a little bit than outside, but it's not going to bring it to 25 degrees. You may say 10 degrees Celsius in the greenhouse. That's not sufficient, right? 25 is what I'm trying to tell you, that optimum. So in such situation, you may have to heat the greenhouse. And you are in an area where there are a lot of hilly regions. So if you are going to build a greenhouse there, most likely you may have to heat at least for a couple of months, maybe December, January months, which will be pretty cold maybe. Okay. So we're going to learn about the heating. That's the reason why it is. But cooling is more important in India than heating. Most of the country is going to get hot, and that's why cooling is important. But we'll talk about heating, and also remind me about the humidity question you asked. So let's look at this cartoon. So here is a greenhouse. Okay. So the greenhouse is hot inside. Let's say it is 70 degrees Fahrenheit, 25 degrees Celsius, and outside let's say it's 0 degrees Celsius, cold air outside. Okay, so the heat is going to be lost from the greenhouse to the ambient outside, because outside is colder than inside. And the way the heat is lost through 4 methods. There are 4 methods. One is conduction, the other is convection, third is radiation, and fourth is infiltration. 4 methods of heat loss. Okay, now let's talk about them. Let's talk about convection. So convection is heat transfer through liquids and gases, fluids. So let's say you have a greenhouse. Let's say this is a greenhouse. This is a warmer region and that's a colder region. The air is going to carry the heat from warmer region to colder region through convection. That's convection through gas, air. Right? With time, everything gets become equalized. Right? If you have a hot and a cold pocket, with time they all become similar. That is happening due to convection. I told you the hot air raises up in a greenhouse. Convection, natural convection, right? Hot air raises up. There's an example. Let's say, okay, then this is hot air here, and here is your greenhouse cover, okay, wall. The hot air comes in contact with the greenhouse cover. The cover is solid material like a polythene or a glass or a polycarbonate. That glass picks up the heat from the air, and then either the glass or polythene, the heat will transfer through the solid material to outside. That is conduction. Transfer of heat through solids is conduction. Transfer of heat through fluids like liquids and gases is convection. Here is an important thing, radiation. This is the loss of heat from a greenhouse in the form of radiation, light, in the form of light. How many of you know thermal glasses? You wear these thermal glasses at night, you can see people. You can see, in army and military, they wear these thermal glasses, isn't it? What are these thermal glasses? Remember this, all of us, everything, we radiate heat. And that heat is coming out of all the living things and non-living things. This is this black body concept. Anything higher than the temperature of the black body, they start radiates heat. That heat is coming out of these things in the form of infrared light, long wave infrared radiation. It's light coming out of us. That's what you're able to see through those night vision goggles. Okay? That's what happens in the greenhouse too. The greenhouse gets heated. All of the things in the greenhouse, the structure, the elements, the plants, soil, all of them are heated up. And the outside is cold, so that heat is lost through the polyethylene. Polyethylene, you learn later on, has the highest thermal conductivity. And that's why in polyethylene, you add infrared blockers. The reason why you want to add infrared blockers is that infrared blocker, when that infrared light hits the polyethylene, that blocker sends it back into the greenhouse. So you hold the heat longer. But we'll talk about that later. That type of heat loss in the form of light radiation is called radiative heat loss. That's a big, big component, especially in cold winter months in greenhouses, polyethylene greenhouses. And the last one is infiltration. Infiltration happens through gaps. The greenhouse door has gap. The wind is blowing. So through the gaps, the heat is lost. Right? We want to close the door, right? Because when we open the door, what happens? The cold air goes outside. It's infiltrating outside. We want to make sure we close it so the room remains cooler. Just like that. You want to keep the room remains hotter, you open the door, it's cold outside, the hot air goes outside. That's infiltration. That's through wind. That's wind that is taking it out. So these are the 4 methods of heat loss from the greenhouse. Okay? So just so you know. Again, all these lectures you probably have noticed by this time, there are some basics to begin with, and then we dive into applied concepts, right? We talk about a little bit about basics, and then we dive into applied concepts. Just like that, even this chapter. So then the question comes, okay, we have to heat greenhouses. How much heat is needed? How much is going to cost me? All of that. So you can do mathematical calculations even for that. Okay. So this rule of thumb is simple. How much of heat is required? Heat required is equal to heat lost. I told you that heat is lost by 4 methods. What are those 4 methods? Infiltration. If you can measure the total amount of heat lost by all these 4 methods, that's the heat lost, and you add back that heat lost to keep the temperature. So the temperature is 70, but these 4 methods made the heat go away from the greenhouse. So you know how much heat has been lost. So you add back the heat, then you maintain 70. So heat required is equals to heat lost. Simple. So now we're going to do a simple calculation. Total heat loss coming from radiation, conduction, convection plus infiltration can be determined by a simple formula. Don't worry about this. I think this is an older slide deck. Yeah, let's get to here. I think this is where I got it. So the total heat loss from all those 4 methods is Q. Okay, let's say it's Q. All those 4 methods, conduction, convection, radiation, infiltration, is Q is given by U times A times W times Ti minus To. It's a very simple formula, by the way. I'll explain everything slowly, but remember that Q, the total heat loss. Once you know the heat loss, you know how much heat is required, right? So we are calculating heat loss as U times A times W times Ti minus To. So what are these different letters? Let's start with Q. We know Q as total heat loss or heat required in watts, W watts. U is the heat transfer coefficient. So every material, polyethylene, glass or polycarbonate, whatever you use to cover the greenhouse, has a certain property. One of that is that heat transfer coefficient. That material is going to transfer these many watts of heat per meter square for a degree Celsius difference between inside and outside. That's what that means. But you get these numbers. These are easy numbers. You get these numbers. You take that number and simply plug in there. Okay. You see here U values. I've given you U values for glass, polyethylene, polycarbonate. So if your greenhouse is a polyethylene greenhouse, what do you take? 6.5. You take 6.5 and you put 6.5 here for U. Okay, that's easy. Next, A. A is area, but it's not the ground area. It's the total surface area. You know what I'm saying? So there is ground area. If you have a 100 by 30 feet greenhouse, that's 3000 square feet ground area. It's a rectangle. But I'm saying that's not ground area. A is the area of the sides, walls, the top, the front and bottom, what we call is the total surface area. You understand what that A is? Very, very important, not the ground area. You have to calculate the total surface area. You plug that value there. Okay? W is the wind factor, and this is where that infiltration loss is coming. W is the wind factor, and W values change by wind speeds. 25 kilometers, you put 1. If it is less than 25 kilometers, don't worry too much about it. You just leave it as 1. Okay? But as the wind speed is increasing, the W value also increases. So if you know the wind speed for the day or for that region, you can plug in that number there. And last things are Ti minus To. Ti is the inside temperature of the greenhouse. 25 degrees Celsius, that's what I want to maintain. Outside is To, 0 degrees Celsius, cold weather. So Ti minus To is 25, 25 minus 0 is 25. You plug in those, you get Q. Simple, right? In this example, if it is a polyethylene greenhouse, you multiply 6.5 times, let's say the total surface area is 10,000, 6.5 times 10,000, W, let's say it's, your winds are about 25 kilometers, so you just put 1, and then inside it's 25, outside is 0, 25 degrees Celsius. You get the total heat loss. You get this number in watts. This is the equation you use to calculate heat required. This is the amount of heat you want to provide continuously every hour, okay, to maintain the greenhouse. To maintain the greenhouse at a certain inside temperature when outside temperature is 0 or whatever that is. So if you know your weather data, like in the next 1 week, you know outside temperatures, you can actually predict how much heat you are likely going to need to add in your greenhouse, because nowadays the climate data is there for sometimes the entire week or sometimes the entire month. So you can plug in those numbers. So before the month happens, you have an idea about how much heat you're going to add. So you know how much you're going to spend on the heating. Okay, that's what it is. Have a question?
So can we reverse both the temperatures if we want to cool the greenhouse also? We can calculate the amount of
The cooling,
cooling
not with this equation. That's a different thing. That's a different equation.
heat retention.
Heat retention? Explain one more time to that to me. You want to retain the heat, right?
No, sir. Actually, I was asking about the cooling.
Yeah, no, you can't use this one for the cooling. It's only for the heat loss, because if you look at this, we're trying to get this equation for all the 4: conduction, convection, infiltration, and radiative losses. There is no radiative loss with cooling, right? It's other way. So that's a different thing. You calculate the cooling from square meter area and solar radiation, eating a square meter area. That's how you know how much heat has been added into the greenhouse. And then from that, you know how much cooling you have to do. That's a different thing. But here is heat being lost otherwise, the opposite of that. We can talk about that. I have some formula for that too. So here is an example, and I think this kind of got messed up. This is not how I put it, but the display is not showing. But you know the math, and if these are the dimensions, you can calibrate the area of the A-frame. Okay, but I think this afternoon maybe we'll do that. Maybe it's an example. But you can measure the A, B, C, D, and E of your greenhouse, and you can get the total surface area from that. Rectangle, square, triangles, and you put them all together, you get the area of that. Very simple. Sometimes I just want to move on. This is not that important, but what I want to get to is to this one. I know there's something wrong with, but we'll get to that. But in any case, this is how you heat a greenhouse. Now you know how much heat you need, right? So why do you need to do that calculation? This is called a heater, unit heater. So you buy this from companies, and when we go to the companies and ask for a unit heater, they will ask you what is the heat requirement for your greenhouse. So you should have done your calculation before, and you go to this person and say, I want a unit heater that generates this many watts of heat. So the recommendation is that you have to choose the worst case scenario for your situation. Meaning, the TO, outside temperature, which is an important factor in that calculation, you should choose a day which has the lowest temperature for the year. Okay, so let's say January 31st is generally the lowest temperature for the entire year. You choose that temperature as the TO value, and you should choose 25 or something like that for the TI value. That's what you want to maintain inside the greenhouse. But worst case scenario, and then calculate the heat requirement in watts. You get a number, and then you go and ask the company to provide you a heater with that capacity, that many watts. Not something simply that, just like, pad area or fan capacity, you've calculated. You should also calculate the heater capacity. And that formula that I gave you, Q is equals to U times A times W times TITO, is mainly used for selecting the heater. Okay, you calculate the watts and you go and ask for the specific wattage. The only consideration is that because you are buying a unit heater and this heater might stay for 10 years with you, you want to really pick up the worst case scenario, the coldest day you will ever see, and that will be the TO value that you will use. That way you are covered completely. There could be warmer days than that, but it's not going to go lower than that. So that's the reason why you should use your worst case situation for that. Okay, so how does this heater works? The same heater, I'm showing you a cartoon here. Okay, that's how it looks. So inside you have a fan. All right, right below is a burner. You see the burner is like a stove, like, so we send fuel. The fuel could be natural gas, I don't know what, probably gasoline, natural gas, anything that you can use. So the fuel goes here, and these are burners. They flame, they light up, and the heat from the flame is sent into these heat exchanging elements. So this is basically a metal rod, okay, sort of like in a line. You're looking at a transverse section, right? But think of it like a metal rod. The burners are there, and this entire sheet of metal is getting heated up. The fan is pulling air from outside, cold air from outside, and that air goes through these heat exchanging elements, and as the air is passing through them, the hot air, the heat is picked by the air, and then hot air gets into the greenhouse. So very simple mechanism. That's what this is. You see this one at the back, you see the fan here. So the fan is pulling the air. Inside there is a burner element, and the heat is generated inside, and hot air is coming into the greenhouse. Very simple mechanism. Any question on that, how that works? Very simple, right? Oh, I don't know why I'm moving. So the main thing is, you see this exhaust, when you are burning fuel, it's going to release a lot of gases that are not so good for plants. You have to make sure that that exhaust is outside of the greenhouse. Okay, if you're going to release that exhaust into the greenhouse, sometimes that may affect plant growth. So if you put the heater here, that exhaust should go outside, or take a tube and send it outside, not into the greenhouse. I've seen people using wood, and they burn wood to increase the heat, but that with that wood, with smoke, there are a lot of other chemicals that you're releasing into the greenhouse that may not be good for plants. Okay, so these are called artificially, generating heat through unit heaters. These are very common in greenhouses in northern latitudes. Okay.
So what is this lower?
This is a lower. You see this? These are called lowers. They open when the fan is running, and they close automatically when the fan is not running. So lowers means they're like fins. They open and close. When the fans come on, automatically they open, so the air goes through. And the fan is turned off, they close. Okay.
So what about the oil-filled radiators, which are also available in the market for heating purposes? Like this will generally affect the carbon neutrality of the greenhouse and will be polluting the environment as well. So what are the better alternatives than this?
Well, you can use electricity, but again, end of the day, it all boils down to economics. You can use coils, you can use all kinds of elements, but end of the day, it boils down to economics. If they are not going to pay off, nobody's going to invest in them. Okay. Yeah, but these are common. They use natural gas. When I said natural gas, it's a fossil fuel, right? We are burning fossil fuels. You can't survive in an economy without burning some. I completely agree. You have to bring down the fossil fuels, but if you only opt for alternate source of energy, maybe we're not there yet. Maybe in the future, not yet. Okay, I got some slides also on that towards the end, but let's see. So going back to your question, so these are fossil fuels and we are burning them, so we are wasting, you know, it's not good for the environment, things like that. Some other methods are there. Okay, so one of the methods is what we call root zone heating, bench heating. I think somebody asked you, right, root zone heating too, right? So here is another example of root zone heating. In this case, what we do is, so this is the greenhouse bench. So you can read this later, but I'm going to explain with this figure. Okay, it makes total sense. Look at this picture. This is a greenhouse bench. We put you know, styrofoam. What do you call styrofoam? Polystyrene is styrofoam. The yeah, thermocol. That's what you call. So those thermocol sheets are there. That's the white color material there. Okay, and then what we do, we have these tubes. I'm sorry. We have these tubes, right? We're running hot water through those tubes. We're running hot water. So we're heating the water, but how do you heat the water? Maybe steam or maybe again natural gas, right? You can't escape from that. Okay, you may have a boiler, but you're heating water. At least you're reducing the amount of heat you will use in this case. We run hot water and then we put plants on top of that. So what's happening is the the heat energy is coming out of these tubes. It is bouncing back from that polystyrene, what do you call thermocol, polystyrene, that's styrofoam, and then it's getting onto the plant microclimate. So if you have a small plants in pots, okay, this system works very well. You are not heating the greenhouse at all. You are keeping the greenhouse cooler, but you are maintaining a warm microclimate around the plant. That's enough, right? It is inconvenient to us, people who are working in the greenhouse, it will be cold inside, but maybe we're there for just 10-15 minutes. Plants are going to sit there all the time, so we just need to maintain their microclimate very well. So we are just releasing that energy through radiation or convection, you know, from those from the water running through those tubes into that area out there. That's called root zone heating. Okay. Another example of root zone heating is this one. I think I've showed you this. So here is an example that I showed you. See, the air temperature was maintained between 60 and 55 degrees, and the hydroponic solution was maintained at different temperatures. You see the effect of root zone temperature. When the root zone temperature is same as air temperature, this is how the plants were. But as we increase the solution temperature, the air was cooler, but the solution, hydroponic solution, was warmer. You can see up to this. So optimum is around 70 degrees. So you can run 70 degrees water and keep 55 degrees air, you still get real good effect. That's again root zone heating. So again, heating the entire greenhouse is one concept using those unit heaters, but you are spending too much money on that. The entire greenhouse doesn't need to be warm. It's just that the microclimate surrounding the plant should be warm. That's what matters. So in order to achieve that microclimate heating, you can resort to root zone heating. I've shown you two examples. One is the water running through those tubes, and the other is in hydroponics itself. These two methods can work very well. There is another method, what we call passive heating. We're not, in this case, we are really being conservative. We don't want to, burn natural gas or anything. We don't want to burn fossil fuels. So we want to use what is naturally available. And one thing is to position your greenhouse such that maximum light gets into the greenhouse during the daytime. That light heats up everything and keeps the greenhouse warm for a longer time at night time. So use the solar energy, basically. Make sure that the greenhouse receives maximum amount of sunlight. The length of the greenhouse should be in the direction of the sunlight in winter. Okay, that way most of the sunlight gets into the greenhouse and the entire greenhouse gets warmer. Here you are not investing on fuel or anything, right? You are just taking the naturally available sunlight too. But this may be useful, but not too much. And so I've talked about the solar greenhouse before in the first lecture. This is what they actually use in China. The solar greenhouse in the northern parts of China is very cool. And so what they are doing is they're actually using the solar greenhouse. Now you see the greenhouse. There is a wall on this side, right? There's masonry wall there. And this is the southern side. So this side gets sunlight throughout the day. So the greenhouse gets warmer during the daytime, and at night time they roll a blanket. I've shown you that they roll a blanket and they cover the greenhouse. So the heat is not lost outside at night time. So they hold the heat inside. Passive, it's not active. Active means you're using fuel. heaters for fuel, things like that. It is a passive method, naturally using the naturally available sun, and in doing so, you are environmentally being responsible, right? There is one more method called geothermal heating. Okay, some parts of the world, and in general, any part of the, if you go deeper into the ground, for example, if you go 20 feet deeper into the ground, even in this part of the world, and measure the temperature at the 20 feet depth, that temperature, you will notice that it will remain pretty much similar throughout the year. So in summer, we get the temperature hot, in winter, the temperature goes down in the air, but inside the ground, at least 20 feet below, the temperature don't fluctuate like that. It always remains similar. And what is that number? It's the average of winter and summer temperatures. So let's say in this region, you have 90 degrees in summer, 50 degrees in winter. The average is what? 90 plus 50, 70 degrees, right? By 2, 140 by 2, 70 degrees. So the ground below at 20 feet will always remain close to 70 degrees Fahrenheit. So now you have a winter which is 50 degrees Fahrenheit, but the ground is at 70 degrees Fahrenheit. Why not tap that heat? Why not pull that heat in the ground and bring it into the greenhouse? That is called geothermal heating. Okay, so what do they do for that? They dig holes around the greenhouse. They put coils at 20 feet depth, and then they blow cold air from greenhouse, and as the air goes through those coils at 20 feet depth, the coils picks the heat from the ground, the air gets heated up, and the hot air comes back into the greenhouse. So you're now not relying on natural gas or fuels or anything. You are tapping into the heat that is already stored in the ground. The other method is go really deep into the ground, 150 feet, 200 feet. As you go deeper and deeper, it's get hotter and hotter. So you can send a coil down, and then cool air goes inside, and the air that is coming back is going to pick up the heat from the ground, and you get the hot air back into the greenhouse. That's geothermal, basically. So you have geothermal and passive methods, which they don't use natural gas, and they're very environmentally responsible. You got to do some investment for that, but those methods are also being used. But for most of the commercial operations in the northern latitudes, heaters, unit heaters are what we use. And for that, you have to burn fuel, natural gas, oils, gasoline, things like that. Okay. I think this is the last slide. Yeah, this is the last slide. Yeah, we're right on time too. So again, I kept the heating piece minimal, but I'll get back to your question in a second. I get the heating piece minimal because it's probably not quite common here. The cooling is the most important thing in this area, so I want you to know everything about cooling. Fan specifications, pad specifications, and considerations of where to keep fans, where to keep pads, the distance and things, all of that very important. So remember those things, okay? And then when you try to cool the greenhouses, and you asked a question about humidity and how do you deal with that, the best way to take care of the humidity is ventilation. You have to continuously, so for in summer you are running the fans, you are getting humid air inside, right, because of the evaporative cooling, but you're also exhausting that humid air outside, right? So continuously you are venting out, you're bringing air from outside to inside, but that air humidity is going up at the pad area because it's getting exchanged with water. So humid air comes inside, but you're venting it also outside. So probably you will maintain whatever the humidity is outside also inside in this situation. But if the outside humidity is high and is causing problem, you have to go for dehumidifiers. Have you heard of dehumidifiers? These are machines you keep in the greenhouse. They basically condense the water, and then they just basically it's cooling. When you cool something, then the water condenses like rain. Like when the water gets to dew point, the air gets to dew point, it rains, right? Just like that, the dehumidifiers also cool the air. As they cool the air, they condense the water, collect the water, and you can reuse that water. So those dehumidifiers options is there, but it's not common in greenhouse. It is more common in vertical farms, indoor farms. I've seen companies which use these dehumidifiers to cool the air, condense the water out of the air, and that way they kind of maintain, because inside a building it can get really humid, right?
So basically, humidity changes with temperature. For example, let's say if
Humidity, relative humidity, yeah.
so let's say inside polyhouse, we are cooling it, then the humidity level would be lower. Let's say then outside air is increasing natural ventilation, let's say we get any outside air, so that is increasing the humidity inside body. So how to understand this situation and how it um, affects plants?
So now we're talking about the effects of humidity on plants. Let's talk about that. So humidity, unlike temperature or light, there is a broad range of humidity, relative humidity, which with a very similar effect on plants. For example, if the relative humidity is between 35% to 65%, plant growth is pretty flat. There's not much of an influence. Photosynthesis is flat. The effect of humidity, and so if you, for example, plot a graph, photosynthesis on the y-axis, humidity on the x-axis, okay, 0 to 100% relative humidity, the graph looks like this. Photosynthesis remains flat at a broad range of humidity and then goes down. So as long as you are in that 35 to 65%, you don't have to worry too much, number one. But then if you go above that, one of the major problems you'll encounter is the pest problem. Insects goes up, their propagation. The high humidity and the temperature will favor their growth, so they multiply rapidly. Bacteria also multiplies rapidly. So that problem is there. Okay, at the lower humidity range, it's a very similar situation like a drought stress. Okay, when the air is really dry, the transpiration increases rapidly. Transpiration is directly proportional to vapor pressure deficit. Vapor pressure deficit is nothing but relative humidity, proportional to relative humidity. So when the humidity is lower, you are forcing the plants to take more water and lose through the stomata. But if the soil doesn't have water, then you are creating a drought scenario for the plants. So lower humidity is more like drought. Between 35 to 65, not much of an effect. Beyond 65, you start seeing bacterial and pathogen related issues. That's how the humidity affects plant growth in general. But how do you get the humidity out? By ventilation, by dehumidifiers, things like that. You can take care of that. Okay, so that's important. Good. All right, why don't you take a break, and we'll meet at 3 o'clock. Again, please, I know some of you couldn't come yesterday afternoon. The tutorials are designed to cement these concepts in your mind. The mathematical equations, the formula, the real world situations you deal with will cement these ideas in your mind. So don't miss tutorials, okay? And also we'll discuss things like, you brought up automation, AIs, IoT, things like that. We'll talk about every day. Come up with a topic for 30 minutes discussion if you're interested. I'm not going to tell you that I can answer everything. I'm not going to claim that, but I'll do my best, okay? And we can discuss. And in fact, I want to hear your thoughts also, so I can learn from you too, okay? Keep that in mind.